All right. Okay, so welcome to Compass Seminars for spring 2021. Today we have Philippe Miron. He got his PhD in mechanical engineering at Polytechnique Montreal, and he's an assistant scientist here at RSMAS. Today he's going to be talking about transition pathways of marine debris and the stability of garbage patches. All right, take it away, Philippe.
All right. All right. So first, thanks for the opportunity, and thank you for everyone who joined this Zoom call. So today I'll be presenting a methodology that I've been working in collaboration with Javier Beronvera at RSMAS and two colleagues from Germany, Lutzi Elfman and Peter Koltai. So I would also like to acknowledge NSF for the support and made all this possible. And we applied recently this method to study transition paths of marine debris, or we can say the pollution routes of marine debris to the garbage patch. So today I'll try to make it as simple as possible. You can stop me along the presentation if you have any questions. And I hope that people can apply this method and use it in all kinds of applications later. So I also wanted to point out that I haven't talked in that long for more than a year, so it should be fun and interesting. All right, so before talking about pathways, we can take a look at the plastic production every year and how much is going into the oceans. So every year, the global plastic production is around 270 million tons. And so this image is from a recent publication from Jumbeck et al. In 2015 in Science. So the global plastic waste per year is also similar to the production. So it's another 275 million tons. From those tons of waste produced every year, about 30% or 100 million tons is located in coastal region, which is defined as 50 kilometers from a coastline. So the author also identified the portion of this coastal plastic waste that is mismanaged every year. And it's about 32 million tons, which means that those are stored in open or unsecured landfill, and they are at more risk of going into the ocean. So we know that each year, about 8 million tons of plastic go into the ocean. And the estimate of surface plastic water, there's wide estimate actually. It goes from 10,000s of tons to hundreds of thousands of tons, and it's very unclear where the vast majority of the plastic is. So we know that it converges to the garbage patch in the middle of the ocean, but it might also end up at deeper, greater depths or in the seafloor. So in the same publication, the author quantify the mismanaged coastal plastic per country. So it may be a little bit hard to see, but it goes from 27% in China, 15% in Indonesia, and between 2% and 5% in countries like Brazil, Algeria, South Africa, and India. So I'll be using this map later so you can remember. And they also order it by region. So keep in mind that from this global mismanaged plastic, the share of East of Asia is about 70% of what's mismanaged. So the questions we are asking is, what is the distribution, the long-term distribution of those debris once they enter the ocean? We're going to try to look at the pathways from the coast to those gyres in the middle of the ocean. And we will also look at the relative strengths of the subtropical gyres, which we mean by this to quantify how much they attract debris. So which one attracts more debris, and is it easy to escape from those garbage patch once you reach them. So to study this, we'll be using the Global Drifters dataset. So since 1979, they tried to maintain a 5 by 5 degree array of about 1,300 drifting buoys. So those buoys have two main parts. The first one is the surface float, which send its location to the satellite. And the second part is a long drogue that's centered at 15 meters that is designed to limit the slip from wind and wave. So to get a better approximation of the dynamic of floating debris, we would actually only consider the trajectories once the drifters lose their drogue. So we call them undrogued drifters. And it's been shown previously that those tend to cluster faster inside the subtropical gyres. And we still have 15,000 trajectories of undrogued drifters since 1979. So it's a perfect coverage and quantity for large-scale modeling. So once we have this database, how can we extract the pathway? So there's a few methods that we could use, simple method. We can just take the drifters, look from where they're launched, and then identify where they're going. But this has some drawbacks. First of all, we're limited by the release locations. So we cannot start from any location on the ocean. We're also limited by an important factor is the drifter's trajectory length. So it's hard to look at pathways between very remote locations as the drifters eventually would stop sending their location after their 2 or 3 year missions. So the second way would be to construct Eulerian velocity fields, but this also has drawback of we lose some resolution due to the coverage and the density. And in the end, we end up most of the time with a well-defined boundary current, but the region of more variability or everything is erased. So the idea and what we suggest to do is to combine the information and not average it of the 15,000 trajectories into a unique Markov chain models. So what do we mean by a Markov chain models? So the classical definitions is a stochastic models where the future events only depends on the current state. So if we look at the one-day super simple transition matrix on the right, we have two states. And if after 10 days, for example, we end up on the state A with 100 pieces of debris, we would have 60% chance or 0.6% chance of staying on the state A and 40% chance of moving to the other states. So this doesn't depend on where those debris come from. It only depends on the current situation and to predict the future events. So from this model or from any type of Markov chain model, we're now talking about probabilistic descriptions, and we'll be looking at probability density and rather than looking at individual trajectories. So every time I'll be talking about probability density, we can imagine that it's a fraction of the plastic that it's going over there. So we obtained this model by discretizing the Lagrangian dynamics that are obtained from the observation trajectories, and we have to assume an advection diffusion process. So in practice, how we do this, we start by putting a grid on the domain. In our case, the grids are 3 by 3 degree, and there are about 4,000 grids on the ocean surfaces. So the second things we have to do is choose a transition time. So for the surface drifters, we found out that 5 days is a good time as it allowed the drifters to leave the 3 degree boxes and connect to the other boxes. And the 5 days is also short enough so we can decompose every trajectories into many little segments. So once we have all of those 5 day segments, we can start building the matrix. So if we take a look, for example, we have 2 bins, 2 boxes, the box I and the box J over there. So at the initial times, we have 5 trajectories in the box I, 3 of them goes over there to the box J after 5 days. So we would have the entry of the matrix Pij would be 3/5 or 60%. So we have to do this for all the 4,000 bins. And remember also that the movements are not only to adjacent bins. The drifters can cross over to 2 or 3 bins depending on their speed and the size of the bin. So in the end, we end up with a 4,000 by 4,000 matrix in our case for the global matrix. So now this transition matrix describes the dynamics of the undrogued drifters, and we made the hypothesis that it approximates the movement of the floating debris. We're still missing 2 key processes in our model. So we have to make 2 modifications to generate a pollution-aware model. So the first process that we're missing is how do we add plastic into the ocean? So we have here an injection of plastic, and on the other side, some plastic reach the coast. So it's output of plastic from the ocean. So we have those 2 processes that are currently not models. And this is how we're gonna model each cases. So the first one, remember the image from the second slide of the share of global mismanaged plastic waste. So we had it by country. Here we're gonna interpolate this map on the coastal bins to have at each bin, we have the share of global mismanaged plastic waste that goes into the ocean. So remember that, for example, if we have 100 pieces of plastic on land, about 70% will be deployed in Asia, 15% on the coast of Africa here, 10% in South and North America, and about 5% in Europe. So this will be how we model the input of plastic in the domain. So now we have to do the second process was the output or the beaching, and we will model it as proportional to the land fraction of a bin. So imagine that if you are in the middle of the ocean, the land fraction is 0 because it's fully ocean in the bin, so you have no chance of beaching. So the beaching will be proportional to this land ratio that shows at the bottom. So now, with the matrix that we had at the beginning, which described the dynamics on the ocean surface, how do we include those 2 input and output of debris? So this is done by what we call adding to the Markov chain a 2-way nirvana. So the nirvana state will represent the land here at the bottom, and we have a input to the land and an output. So what goes out of the ocean to the nirvana is the beaching of plastic, and this plastic will be re-injected in the chain according to the distribution of the plastic waste mismanaged. So if we look at the matrix form of our chain, so imagine that the PO here represent the ocean. So this is a 4,000 by 4,000 matrix. We add 1 line and 1 column to this matrix. And then those 2 PO to nirvana and the nirvana to the ocean are vectors that are defined according to those 2 distributions. So what's important to understand now is that we're looking at a closed loop. So the plastic is injected in the ocean. If it beach, we re-inject it according to this distribution. And we are looking at longer time how this plastic is evolving on the ocean. So now let's take a look at the transition path theory. So this is what's going to allow us to extract the pathways of those debris. So first, the theory was first developed to identify and understand rare events. It was actually developed for chemical reactions. So in chemical reaction, you have a reactants and a products. When those 2 are combined, you have a reactive events. And the path between those 2 are called reactive trajectories. So in our case, we're going to be using this to identify ocean pathways. And So remember that to find those pathways, we have to fix two things. So we first fix the source and the target, so the source A and the target B. With the method, if we have a trajectory that's going like this around the domain, following the probabilities, we're going to extract the red pieces automatically using the method. So it's also possible to restrict those pathways. So for example, if we want to avoid the state C, we can restrict the pathways and say, okay, we're starting from the source A, reaching the target B, but in this time we cannot touch the state C. This will be used in the future calculation. But always have this image in mind, and we should all think about the source A and the target B for the following results. So the target, so the source, we know the plastic is injected from the coast. Now we're trying to figure out where is the target, where are those garbage patches, and which bins should we select to look at those pathways. So to do this, we ran the model for 10 years, starting from the nirvana states. So remember that the nirvana re-inject the pathways and it's connected to the coastal polluting bins. So to calculate this evolution, it's a simple vector matrix product. So we start with a density in the nirvana state. We simply multiply it once and we get the density after 5 days. So on the right, I did it multiple times and we have this evolution for about 10 years. So what's interesting to note is that there's a convergence to the main subtropical gyres. So we see in the North Pacific, South Pacific, North Atlantic, and South Atlantic. Another thing is that in the Indian Ocean is a little bit more diffuse and weaker. And this was also pointed out by Van der Meen and et al. In 2019. And they argue that there's not a clear defined garbage patch in the Indian Ocean, but we can still see some accumulation here. And finally, we have two interesting garbage patch that are not in subtropical gyres. The first one in the Bay of Bengals, east of India, and the second one, it's south of Nigeria in the Gulf of Guinea. So the target will be selected where the pollutions is maximized, and more precisely in those 7 red squares. So we will be using those squares to identify pathways from the coast to the different garbage patches that we just identified. So before that, just to look at the accumulation into those subtropical gyres, this is a 150 years simulation, and at each time step, I'm looking at the density inside the red square that we just identified. So the interesting thing to see is that it takes about 70 years for the system to become in equilibrium. And it's in agreement with the recent observation. There's more plastic in the North Pacific Ocean. The second one is the South Pacific Ocean, which takes a bit more time to ramp up. And in the last one is the Indian Ocean, which is, as we will see later, it communicates more to the other basins. All right, so let's go back to the theory. The basis of the theories are the commuters. So the commuters represent the probability to reach the target B, so the state B, before coming back to A, or the opposite in backward time. So let's see this example. If we start the source in the nirvana states, and we put the target in the North Pacific gyre. So we are starting from the coast, and we see that the probability of reaching the target increase and is maximum on the target itself. So that means that where it's 0, there's no chance of going from this location to the target without touching the coast. In backward time, it's the opposite. So we are starting from the target and we are trying to go back to the, we are starting from anywhere in the domain and we're trying to go back to the coast without going back to the target. So actually what is important to remember is that the current between the coast and this target is the combination of those two committers, the forward committers in forward times and the backward committers in backward time. So if we multiply those two, we see that here it's 0 and it's only larger than 0 in the North Pacific. So we should expect current only in the North Pacific. And this is actually the main result. So the reactive trajectories, or the current that we obtain, is the most likely transition channels from the source A. In this case, the source is set to the coastal bins inside the target, or which is the North Pacific gyre. So as I just said, the current is calculated in this fashion by multiplying the backward committer and with the forward committer and the transition matrix that we just calculated. Okay, so this was a simple example with one target, but we can also, before going into that, there's also properties of the reactive trajectory. So there's two important properties that we're going to use to quantify the current and to quantify the strength of those garbage patch. The first one is the transition rate. So this is it can be seen as a flux or a transport from the source to the target. So let's take a simple example. If we have a transition rate of 0.1, it means that at every time step, 10% of the debris are leaving the source and are on their way to the target. So this is calculated by the summation of the current from the target to the domain. But since it's a flux, this values is actually equal to what's entering the target. So what's exiting the source is equal to what's entering the target. So as I said, it can be interpreted as a flux or as a transport. So for example, if we know how much trash is released in the ocean every year, we could multiply by the amount of tons, K, and this will give us how much trash is entering the target every time step. So in our case, every 5 days. So those values are interesting to see to quantify which pathways are more probable and actually the strength of the pollution routes. So finally, the second properties is the mean duration of the reactive trajectories. So this is actually obtained by dividing the probability of being reactive and the rate that I just explained. So in the case of the example that we just saw, there's a mean time of 7.3 years to leave the coast and reach the North Pacific gyre. Okay, so as I was saying, now we had only one target, but we are interested in looking at the connection to all of those patches that we identified. So there's actually 7 targets. And in this case, we set the source to the nirvana state, and the target B is set as the union of all the garbage patches. So again, we have the forward committer that maximize around those 7 red square. And in this case, what's different is that the forward committer is only 0 closer to the equator and the Arctic. So it's not 0 in the southern hemisphere. So if we multiply those two again, we obtain the current from the coast to all of those garbage patches. And the magnitude is plotted, the color is actually the magnitude, and it's the transition rate that I just explained. So just note that this goes until 10 to the minus 4, and we'll see later that it's more important than some other cases. So okay, there's a few things to notice on this one. So the pathways to the main subtropical gyres are much larger than in the 2 bays that we identified in the Bay of Bengal and the Gulf of Guinea. So this suggests that those are filled with close nearby source of pollution, and the garbage patch actually attracts debris from further locations. So there's also an important zonal reactive channel that leaves Eastern Asia and converge to the North Pacific subtropical gyre. Still in the Pacific, but in the southern hemisphere, we can see that the South Pacific subtropical gyre attracts debris from the coast of South America, but also from all the way from the Indian Ocean. So it goes with the Antarctic circumpolar current all the way across the Earth and converge into the South Pacific subtropical gyres. So in the Indian Ocean, it's a bit more complicated, and we see that there's no clear, it's a bit less clear convergence into the gyres. So we have a lot of current that are exiting and actually entering here in the Southern Atlantic. And as I was just saying, also to the Pacific Ocean. So now one thing we're going to look at is the interconnectivity of those main subtropical gyres. So to do this, we're going to change the target to one of the subtropical gyre, the source, and the target will be all of the others. So in all of those images, the source will be in black and the target will be the red squares that are shown here. So first I started with the two subtropical gyre in the northern hemisphere, and we can see that there's a north-south connection between the gyres. So if debris are able to escape the North Pacific gyres, they mostly converge in the South Pacific. And the same thing is true for the Atlantic Oceans. So again, note that the magnitude of this current is much smaller than the one we had before, which was 10 to the minus 4. So those currents are less probable. So now if we look at the same figures, but for the southern hemisphere, we have quite different pictures. So instead of a north-south connection, in this case, we have more of an east-west connection through the Antarctic circumpolar current. So if we start from the Indian Ocean here, it follows the Agulhas current, which then retroflex, go south of Australia, New Zealand, to converge in the South Pacific. And there's also some current that goes with the Agulhas current in the South Atlantic. So we see this for most of those garbage patches, and the magnitude is a bit higher, so those currents are a bit more probable than the one that we just saw north-south for the northern hemisphere. So again, I wanted to highlight the importance of the Antarctic circumpolar current that plays a big role in those exchanges. So the last plot for this interconnectivities is actually from the gyre to the coast. So basically the opposite of when we're putting trash to the ocean. Now it's what can happen if in the event, for example, of a strong wind, if debris manage to escape one of those garbage patches. So in this case, the source are set as all of the subtropical gyres, and the target is set as Nirvana, which is connected to those red bins. So remember that those red bins are where debris can beach. So here it's all the small islands in the Pacific, so it's not an error of the script. And so the first thing to notice is that the current are still pretty strong at 10 to the minus 5, and they are mostly maximizing in the northern hemisphere. So this tells us that the connection from the northern hemisphere is mostly going to the coast, and compared to the southern hemisphere where the connection is between patches. So an important something very important that we found out is that the North Pacific attracts the more debris, as we saw at the beginning, but actually the South Pacific garbage patch has a higher retention rate, which means that once you're in the South Pacific, it's very hard to get out. So we said that it's also more stable than the other garbage patches. So this figures is a summary of the previous 5 plots. And so for every row of the tables, we have the source is the left label. So if we take an example of the North Pacific Ocean, and the targets are set as all the other columns. So we can see that there's 3 things that we can notice. The first one is that the magnitude to Nirvana and from Nirvana is much higher than the connectivity between the garbage patch. So it's 100 times, 2 orders of magnitude. So the second thing that we can notice is that the southern hemisphere garbage patch are connected together. So as I said before, the Indian Ocean, if we look at where it maximizes, we have higher values in the South Pacific and the South Atlantic. Same thing for the South Atlantic. It converges more to the South Pacific and the Indian Ocean, and the South Pacific Ocean converge again to the South Atlantic and the Indian Ocean. This is very different from the Northern Hemisphere subtropical gyres that mostly are converging. If they converge to something, is only to the land. So they have very limited interaction with other garbage patches, which is an interesting result. So another result that we can get, as I explained before, the expected durations of those trajectories. So if we want to know in the Pacific Ocean, how long does it take to go from the coast to the garbage patch in the center? For this, we set individually the target to the Nirvana to each of the garbage patch. And we get expected durations of 7.3 years for the North Pacific gyres, 8.6 years for the South Pacific gyre, and then about 4 years for the North Atlantic, South Atlantic, and Indian Ocean, and much shorter times for the Bay of Bengal and the Gulf of Guinea. So the larger time in the South Pacific is probably due to the fact that debris from further location can converge, as we saw from the Indian Ocean, south of Australia, and even this from south of South America. So in this case, we put the target to each of the garbage patch individually, and we restrict to not touch the other patches. This is to avoid having trajectories that are too long and not really representable of the reality. In this case, we are focusing on smaller trajectories that are in the basin where we are interested. So one of the latest plot that I wanted to show is the domain of influence and the residence time associated with all of those garbage patch. So we call this a forward commuter geography, and it's to quantify the domain of influence, as I just said. So how we do this is by calculating the probability of reaching each garbage patch in a bin that is indicated by the red square. So again, we start from the coast and we calculate the probability of reaching, for example, in this case, the North Pacific garbage patch. So we do this for each of the 7 patches. So we get 7 forward commuter. And then we assign each bin according to its maximum value. For example, the bins in the North Pacific are going to converge to the North Pacific subtropical gyre here, the red square. So we're going to combine them together. And we do this for all of those 7 regions. So we can decompose the world ocean into 7 basins. So those basins we expect, so if we start in one of those bins inside, for example, the basin in the South Tropical Gyre, we expect that the pathways are going to converge inside the red square in this region. In this plot, the colors represent the mean residence time. So I didn't go into details how we calculate this, but it's simply put, it's the expected time to get out of this domain, or the residence time, how long we can expect to stay inside this region. So we can see that the South Pacific gyre has a larger residence time at 15 years. The North Atlantic and South Atlantic are almost the same color because they have very similar residence time at 7 and 8 years, and similar for the North Pacific gyres. And the Indian Ocean is much smaller at 1.5 years, which again is an agreement that the subtropical gyre in the Indian Ocean is weaker and the debris are most likely to get out of this region. Again, the two other the garbage patches identified in the Gulf of Guinea and the Bay of Bengal have much smaller residence time, where debris converge very fast to those red squares. So in conclusion, we identified the reactive pollution routes, and those could be used as targets for future cleanup efforts instead of only focusing on the garbage patch itself. So we also observed that the North Pacific subtropical gyres attracts the most debris, and it's consistent with earlier assessment, but we found out that there are fewer pathways out of the South Pacific gyres, which is a new result. We also identified yet to be discovered or yet to be observed garbage patches in the Bay of Bengal and the Gulf of Guinea. And this methodology can be useful for many other types of applications. We currently have other paper in the work on sargassum tracking and deep water pathways in the North Atlantic. So I put some reference that you can take a look later if you're interested. And this is my final slide. So the first link is the link to the presentation, if you want to take a look. The second link is our group website. The third link is my GitHub, where you can find the code that I've used that has been used in 7 publications so far. And there's also a folder especially for this publication, and you can reproduce all the results that you just saw in this publication, in this presentation. The paper is on the archive currently, but it's been accepted in CHAOSS, and it should be published in the upcoming days or week. So thanks for listening, and thank you. I'll take any questions now.
Okay, thank you very much. If someone wants to ask a question, please turn your microphone and camera on and try to ask it into the camera, and then maybe we can look at the questions in the chat. But I prefer live questions. Claire, do you have a question?
Actually, I do. I think this is extraordinary work. It's really well conceived and well done, and it's important. So yeah, congratulations on this work, Philippe. I have some questions that are more like technical questions about, what is the frequency of the nirvana? I think it might be 5 days because it's your integration time or time step. Your time step is 5 days, right? So
yeah.
Yes, and so my question was like, you assume that the nirvana is not uniform, but have you tried to do the model? I know it's a lot of modeling, but to do with a uniform situation, because there is a lot of speculation in where the origin of this plastic is.
Yeah, the answer is we actually did. And so the results are similar from the current perspective, but the magnitudes are not. So we were trying to find a more adequate way of distributing. I'm not sure about, so we found this publication in Science, so we decided to base our result on it because it's the best observation we could get.
Mm-hmm. Yeah. So
but it's not that
is there like the conclusion are the same? It's just like the magnitude of the current is different?
Yes, most of the difference is in the magnitude.
Yeah. So is there any way to validate that, or no? I don't know.
So I'm not sure what's, so we decided to go with this distribution as we thought it was a more fair representation. Since, for example, if we start, we put it uniformly, we're going to be distributing plastic from Antarctica or like north of Canada where there's no one. So at first we thought of doing it simply by the population that lives around the coast, but we ended up going with this idea of the shared of the global mismanaged coastal plastic.
Yeah, that's great. So if I may, because I don't want to take all the time, but I have just one other question that has to do also with initial conditions, this time with the location and number of drifters in the ocean on Earth. I think that there's some bias there. Do you think it would have changed because of the fact that there's no so many drifters in like the northern currents?
Yeah, of course it changes in some regions, especially there's one region, there's actually no drifters that are crossing in the in between all of the islands here near Indonesia. Mm-hmm. And if we look at the distribution map of the mismanaged plastic, this is a important location, but we have no drifters. So yeah, we have to do with the observation that we have, sadly.
Yes, of course, but I think your paper is really important because it shows that this is really an important region, and the data is not quite there, so there needs to be more drifters in that region. All right, so I don't want to take time again, but yeah, good job. I mean, it's amazing.
Thank you.
Okay, Mathieu, I think you were the second one who showed up.
Hi everyone, thanks Philippe, very nice presentation. My only question was, I was curious, we see the transport south of Africa going eastward. There is no Agulhas leakage or no Agulhas current, so I was wondering if that was because of the sampling from the drifter database or from physical processes. Do you have an idea?
So I'm not sure. I think it's because the bins are pretty big and it's next to the coast. So maybe if I remove the coast, we could see a little bit clearer pictures. But if you look on the right side here, you see the Agulhas current going up here on this side. But yeah, if you look here, we mostly see the retroflexion, but there are some current that's going westward also.
Yeah,
but it's localized closer to the shore.
Okay, thank you.
Okay, Yugao, do you have a question?
Yes. So it's a more general question. Do you consider the only the plastic that's non-biodegradable like type of materials, or do you consider all garbage as a whole?
Yeah, in this case, we don't have a degradation of plastic or any other mechanism like this. So this could be something that could be included in the models. So for example, every time step, we could remove some plastic that are biodegradable and see how it affects. But yeah, in this work, we're assuming all the same density of plastic. We're not assuming that they are not any size. We're just assuming that they have similar dynamics as the undrogued drifters also. So we're not modeling very small pieces of plastic either.
Yeah, okay, I see. Another question. Is there a possibility that those garbage can end up in the Antarctic?
Possible. So we
Oh.
so the thing is there's also not that many drifters in the Antarctic. So probably the this is one of the negative point, because if you look at the beaching, which is the bottom plot here, it's only proportional to the land fraction. But if we don't have drifters that go close to land or close to ice in Antarctica, we don't have the beaching that is modeled over there. So it's possible that it's higher in this region.
Yeah, okay.
Yeah, that's something we
Thank
should
you.
have pointed out.
Thank you. Very nice study. Thank you.
Okay, I see Renelis Perez.
Yes.
Want to...
Hi, very nice presentation. I was just wondering about, and you might have said this at the beginning, about the origin of that terminology of nirvana. Very interesting.
Yeah, so maybe I said it but probably too fast, so I can repeat it. So the nirvana represent the land. So when I said I start in nirvana, it means that so the next step in the model is going to be injected in the ocean according to the top distribution here. So the nirvana is connected to all of those bins, and share is the magnitude is shown over there.
Thank you. Yeah, and I meant just esoterically, like that, using that term, that word to describe that concept, where that originated.
We were just thinking about no, I don't know. We're just thinking about the debris are getting out, they come to nirvana, and then they are re-injected into the world, and they come back.
Yeah, then there is something from Rick Lumpkin. I guess he doesn't want to speak. Oh no, there he is.
Yeah, I'm ready. I'm willing to. I just a quick comment. You know, I've been on a Navy vessel right on the coast of Lagos, Nigeria, and I've never seen so much pollution in the water. To back up that being a kind of a mini gyre area, they had to put divers over the water every couple of days to clear garbage out of the propellers, which is unusual for them. So yeah, that it very much looks like, you know, what you're showing in the simulations. And then a question for you: the statistics of this kind of transition matrix approach don't include interannual variability, and we know, for example, that in 2009-2010 extreme El Nino, or excuse me, extreme NAO event, that the Sargasso Sea may have been sort of fleshed out and led to the inundations later on. How would you speculate that this kind of interannual variability might affect your results?
I would expect that it could change a lot from year to year. Here, in this case, we are taking all the 15,000 trajectories and putting in a single model. So I didn't think about El Nino states. So yeah, that's something we could look at, separate the data into La Nina and El Nino states and see, and run the model again and see how this affects and how the impact on the current and the fate of the distribution of the debris. Yeah, that's a good point, Renelis. And I think we have enough data to do this with the Global Drifters database.
Do we have more questions or comments? Maybe not. So I can just say thank you again. Very nice presentation. You attracted 25 people on a Thursday afternoon, which is a pretty good number. Thank you all for coming. We will have the next seminar as soon as tomorrow morning at 11 with Mao Feng Liu, and I hope to see most of you there again. Have a good afternoon.
Thank you. Have a good one.